So today I want to begin our discussion of revenue maximizing auctions. So revenue is a topic we really haven't touched on yet in this class. Ever since we began with the Vickery auction, we've been focused on the objective of social surplus maximization. So that's what we've talked about so far. We've designed for a number of different application domains, DSIC auctions which maximize surplus. So it's not that we haven't seen payments. There are payments even there in the Vickery auction, but the point was not really to raise revenue per se. We had payments only to encourage people to do the right thing, only so that we could get a DSIC implementation. Revenue in some sense was a side effect of the incentive constraints. So today we want to talk about when raising revenue is a first order goal. So let me explain just for a second why I started out by talking about surplus maximizing auctions. And one is it's just something you should know. So it's one of the most fundamental objectives in the theory and practice of auctions. There are definitely real-world scenarios where more or less what you want is to do surplus maximization. So one example would be when something like a government auctions off a public good. So you see that with these auctions run by the FCC to figure out which telecom should own wireless spectrum, for example. Then, revenue is a consideration for the government in those auctions, but still the first order goal, more or less, is surplus maximization, not revenue maximization. Another thing is in competitive environments, it's thought that you generally are forced to surplus maximization, because if you don't maximize the surplus, one of your competitors will. So sometimes it really is what you want. But a second reason that I started with surplus maximization is pedagogical. So it turns out surplus is special in a technical sense. And that made it easy to start with. And the reason it's special is because you can maximize surplus in an unusually strong sense, in a sense we will not be able to do with revenue. One way that this would be described is we can maximize surplus even ex post. And essentially what I mean is just, like I said many times in the past, we were designing these auctions that had the cool property that they were maximizing the surplus as well as if they had known all of the private information, the bidder valuations up front. So even if after the fact I told you what everybody's valuations were, you'd be like, yeah, whatever. I mean, I did the optimal thing anyways. I already figured out the valuations. Thank you very much. Okay? So surplus can be maximized even in the strong sense as well as if you knew the private information in advance. A different way of thinking about this is you get the DSIC, the incentive constraints, for free. Okay, they impose no surplus loss. Okay? So let me now do a very simple example. It may seem stupid, but it's actually very illuminating, and I'll drive home this point that profit maximization is just not as simple to think about as surplus maximization. So I want to look at a single item auction with the additional simplification that there is only one bidder. Okay? So one item, one bidder. So the bidder has a private valuation unknown to the seller. And there's one item. Now, when there's only one bidder, turns out the design space, the space of all auctions you could run, is not that rich. There aren't that many different things you can do when there's only one bidder you're interacting with. Essentially, all you can do is offer that bidder a take it or leave it offer. Those are the DSIC mechanisms. These are also called posted prices. It's not going to matter, right? DSIC auctions, you don't care, generally. So you can think about it either way. So you walk up to the bidder and you say, look, but you show them the item, you put a price tag on it. You say, take it at this price or not. Okay? So in a take it or leave it offer with a posted price at a value of R, as the seller, your revenue is going to be one of two things. Okay? So what happens if it turns out this unknown valuation V is at least the take it or leave it offer that you gave the bidder? What's your revenue going to be? How much money will you make? R. And otherwise, nothing. Okay, they walk away. So that's kind of the space of possibilities for one bidder and one item. You can also randomize over posted prices. That's not going to change the point I'm making here. Okay. So suppose this was your situation and you wanted to maximize the surplus. How would you choose R? You didn't care about how much money you make. All you want to do is sort of have the greatest global good possible. 0. Good. Easy problem. And if you think about it, that's basically what the Vickery auction would do. Okay, there's no second bidder, but you could think as if there's a second bidder who bid 0. Okay? So to max surplus, just set R equals 0. Okay? And notice the answer did not depend on the private valuation V. Okay? We don't actually care what this private information is. What we should do is unequivocally defined. Okay? That's the sense in which we can even ex post maximize surplus. What if we wanted to maximize revenue? So let me give you sort of an unreasonable, easy version of this question first. What if we wanted to maximize revenue ex post? That is, what if we actually knew V by our telepathic powers? We knew V in advance. How would we set R to raise revenue? We just set it to V, right? We'd set it to be as high as possible, subject to the bidder actually taking it. That would make us the most money. What if we don't know V? How should we set R? You get to set it once. So in other words, the revelation principle says that boils down to figuring out the last price you're willing to offer. So what's that going to be? It's actually not even really clear how to think about that question, right? It's not even clear it's a well-defined, meaningful mathematical question, all right? So we have some kind of fundamental work to do to get a theory of revenue maximizing auctions up and running. Okay? It's not going to be as simple as surplus maximization, but I'm happy to tell you that in very reasonable senses, it's a well-solved problem. So that's what we're going to learn starting today. Okay? So upshot. For revenue, unlike for surplus, different auctions do better on different inputs. So for example, with one bidder, the auction which posts a price of 20, well, that's going to do really great on inputs where the private value is close to 20. Wow. And at least 20. And it's going to do extremely poorly on inputs that are close to 20 but below 20. Okay? And on those inputs, auction that's a posted price of 15 will do better. Okay, so which auction is better? It depends on the input, and you don't know what the input is. That's exactly what's private. Now, as computer scientists, this is not a quandary that is foreign to us, right? When we reason about algorithms, we face exactly the same problem. If I ask you which sorting algorithm is better, A or B, well, sometimes the answer is obvious. Some sorting algorithms are just stupid. But if it's like insertion sort and quicksort, it's going to depend. I mean, some inputs quicksort will be better, some insertion sort will be better. Same thing with heuristics for NP-hard problems. Traveling salesman problem, what's better? Local search, integer programming, it's going to depend. Depends on your input class. Okay, so this is not a new problem, but that doesn't mean it's an easy problem. So what we need then to even sort of get started is a model which tells us how we should reason about trade-offs between our performance on different inputs. Because whatever auction we wind up advocating will do well on some inputs, worse on the others. So how are we going to argue that our auction is better than some other auction? Whoops. There are multiple such models that have been well studied, but today we're going to discuss the most classical and most well studied one, which in economics they would call a Bayesian model, Bayesian analysis. In computer science you generally call it average case analysis. That is, we will posit a distribution over inputs, that is a distribution over the private valuations, and seek to do as well as possible on expectation with respect to those distributions. Okay? So to be concrete, I'm going to keep working with single parameter environments. The same sort of generality at which Meyerson's lemma applies, as we discussed last week. Though I encourage you in this lecture to go ahead and think about the special case of single item auctions. That's already a very interesting, motivating example. And what's going to be new is that VI, the private valuation of participant I, is drawn from a distribution f sub I. Okay. So just to jog your memory, remember a distribution function, if you plug in some value z, what this spits back is the probability that the realization is at most z. Okay, so the range here is 0, 1. Okay. I'm going to assume, just a couple technical points, I'm going to assume that our distributions have densities. Little f sub I, and bounded support. So let's say valuations lie between 0 and some finite upper bound V max. Okay. Also, the FIs need not be the same. You can have some bidders that are aggressive, some bidders which are cheapskates, but they should be independent. Okay. For the theory we'll discuss today, they cannot be correlated. And they also should be known to the mechanism designer. Right, so the whole point is we're going to optimize with respect to these distributions, and of course to do that we need to know what the distributions are. So known to the mechanism designer. The mechanism designer knows the distribution from which a value is drawn. It does not, of course, know the actual realization, the actual valuation. That would trivialize the problem. Maybe I know you're uniform from 0 to 1, but I don't know what the draw actually is. Is there a question?
So each bidder has its own distribution?
Correct. So distribution f sub I is associated with bidder b sub I and its valuation v sub I. All right, so the mechanism designer needs to know these distributions just to reason about trade-offs between different auctions. So what about the bidders themselves? Well, it depends on the model. I want to keep things simple today, so I'm going to continue to discuss only DSIC auctions, only auctions where bidders have dominant strategies, although the theory we'll talk about today actually generalizes very easily beyond those. But when auctions have dominant strategies, then the bidders either don't need to know or they really don't care about the distribution from which other valuations are drawn. They have a dominant strategy, it doesn't matter what else is going on. Okay? So for today, only the seller really needs to know about the distribution or have an estimate of the distribution. For example, if these are some sort of internet auctions, there's a good chance you have piles of data that you've built up over time. That's where you'd get these distributions, these f sub i's from, okay, from looking at your logs of what people have done in the past. Okay. So let's now notice that this problem that we were totally unable to think about 5 minutes ago, we can now reason about almost trivially now that we've posited these distributions. So back to the one bidder case. One item. And this bidder's private valuation is drawn from some known distribution capital F. So now, for a given auction, when we want to know how well it does, we can just look at its expected revenue. And again, the expectation is with respect to this private valuation, V. So the expected revenue of some posted price R. Well, the easiest way to think about it is it's so we know that if there's a sale, right? In the event that there's a sale, we know we're going to make R dollars. And what does that have to get multiplied by? Well, sometimes we're going to have a sale, sometimes we're not, right? So this needs to be multiplied by the probability of a sale. Okay, and so the probability of a sale is just the probability that the value, the private value, is at least the posted price R that we chose. So capital F's tell you the probability of something be at most a given value. So what we want here is 1 minus capital F of R. And again, the reason being is that just by definition, this second term is the probability that V is at least R. Okay? And this is revenue of the sale. So that's a simple expression. If you told me some distribution capital F, I could now just search for the best R. Okay? And whatever R makes that number as high as possible, that would be the optimal auction, the revenue maximizing auction, with respect to this distribution capital F. So for example, if V is drawn from a uniform distribution on 0, 1, a simple calculation shows that best R is 1/2. Okay? So what would be the revenue of this posted price, for example, if V is drawn uniformly from 0, 1? So how much money would you make? What would be your expected revenue with this posted price in this distribution? 1/4, right? You have a sale half the time and you make half a buck every time it happens. Okay? And some terminology that'll come up later is the notion of a monopoly price. And that is just the value of R that makes this number as large as possible. Okay? So that's a monopoly price. Okay? So for this distribution, the monopoly price is 1/2. All right, so good. So at least for this sort of very silly example, which I used to sort of illustrate that we needed a sort of richer model, we know what to do. But we probably don't care that much about one bidder settings, right? We'd like to do something a little more interesting. And it gets interesting already with 2 bidders. All right, so I'll leave the computations as an exercise, but let me just sort of tell you some results. So now let's just make it so there's 2 bidders, one item, and both the valuations, these are going to be IID bidders, so both the valuations are drawn from uniform 0, 1. Excuse me?
Does it matter whether or not the bidders know that?
The bidders are, speak up.
Does it matter whether or not the bidders know that?
Know what?
That, like, the other bidder is drawn from that.
As long as we're considering DSIC auctions, no, because you have a dominant strategy. So, but let's think about it from the designer perspective, right? Suppose you know there's 2 bidders and your model is that their valuations are drawn IID from uniform 0, 1. With 2 bidders, there's more auctions you can start thinking about doing. So for example, the Vickery auction now makes sense. So you can just run the Vickery auction. Again, the point of the Vickery auction is to maximize surplus, but it inadvertently generates revenue. We can see how much we get. So Vickery, by a simple calculation, which I'll leave to you, the expected Vickery revenue turns out to be 1/3. Okay? You just allocate to the high bidder, charge the second highest bid. Okay, you'll make some money. You'll make 1/3. So what else could you do? Well, you could do a few different things, but the first thing you might think about doing is, in the same way that we sort of had this auxiliary price for the one bidder case, we could augment the Vickery auction with a reserve price. Okay? And in eBay auctions, for those of you that are familiar with them, these are just opening bids. Okay? So when there's a reserve price, it just says, look, for me to even consider you, your bid has to be at least as high as the reserve. Okay? Moreover, what's the benefit of the reserve price? This can potentially push up the amount of money paid by the winner. So there's going to be a trade-off. If we add a reserve, and it's going to be a reserve of 1/2, two things happen. So first of all, there'll be cases in the Vickery auction where we would have made some money. Okay, if the two bids were 1/3 and 1/6, you'd make a 1/6. If you had a reserve of 1/2, you would filter both bids. You wouldn't sell the item. You'd make nothing. Okay, so that's an input where you do worse with a reserve of 1/2. On the other hand, if you get one bid of 2/3 and one bid of 1/3, in the Vickery auction, the winner is charged 1/3. But if you had a reserve price of 1/2, you filter the 1/3 bid, and that's now the price charged by the winner. Okay, so just like in eBay, the opening bid, you're never going to pay lower. You're never going to get away with paying lower than the opening bid. When you have a reserve price, the winner will never pay less than the reserve price. And if the reserve price happens to split the highest bid from everybody else, then that's a win. Okay. So if we add a reserve to the Vickery auction, we'll do better sometimes, we'll do worse sometimes, and the distribution tells us how to average to figure out, do we do better overall? Turns out, in this case, with a reserve of 1/2, we boost this revenue a little bit, from 1/3 to 5/12. So the pro of having higher prices with one winner outweighs the con of sometimes not allocating the good. So far, the only point I've made is that there's multiple natural auctions you could run, already with two bidders in one item, and some do better than others in expectation. But the obvious question is, who says this is the end of the line, right? Can we do better than just a simple Vickery auction with a reserve of 1/2? Maybe some other reserve is better. Maybe some totally different auction format is better than this one. Who's to say? So if we want to be ambitious, then, the goal should be for any situation, any single parameter environment, not just single item auctions, any distributions, not just ID distributions, to characterize what the optimal auction is. Okay? Figure out the auction that maximizes the expected revenue with respect to the distributions F1 through Fn. And again, for this entire lecture, when I say optimal auction, I mean maximizes expected revenue. Expectation with respect to the given distribution over the VIs. So this is what we're going to do. Okay? So I will give you such a characterization in the rest of this lecture. Okay? That's the plan. So step 0, and just to sort of remind you of an important simple result from last time. So, our concern should be, it's like, man, it seems like there's a lot of different auctions you could run. It's like seems like a crazy big space. Who are we to think we can actually figure out what's the best point in that space for any environment and any distributions, right? So the first thing I want to point out is, it's still going to be the case that there's lots of auctions out there in the world, but at least we can funnel in on just these simple 3-step auctions we've been discussing all along, these sealed bid or direct revelation auctions, where you have an allocation rule X, and a payment rule P, and truth-telling is a dominant strategy. That's all we need to worry about. The reason is the revelation principle. So remember what that says. That says you give me any auction with guaranteed dominant strategies, I will give you an equivalent auction. In particular, the revenue will be equivalent, so that truth-telling is a dominant strategy. Okay? So that's the first thing to realize. And again, remember a generic such mechanism. We write by the allocation rule, which chooses who wins, and its payment rule, which chooses what they pay. And because we're only going to be thinking about these mechanisms, and this is why, for the rest of this lecture, I will never again write bids on the board. Okay? For the rest of today, I will always assume that the bids are just the valuations as justified by the fact that all auctions under consideration are DSIC. Okay? So the valuations, of course, are unknown to the mechanism, but if they're the same as the bids, then it still makes sense to write V. Okay? All right, and just to be clear, what is the revenue of such a direct revelation mechanism? Well, it's just the sum of the payments. Okay? So the payment rule on a given bid profile, which again, I'm just going to write the valuation profile. I look at the money paid by each of the end bidders, and I sum up. Okay? So this is a number associated with every input, every valuation profile. This is what we want to maximize on average. So again, with expectation with respect to the vector V. All right? Yeah?
How do we know that options with dominant strategies are the best one?
Excellent question. The question was, maybe we're losing tons of money by this restriction to DSIC. Right? So like maybe the first price auction kicks the second price auction's butt. Okay? And you're right, from what I tell you today, we will not rule out that possibility. I'm giving you, in effect, a special case of the general theory for DSIC mechanisms, just to sort of slowly build up your intuition and understanding. I'm happy to report that the auctions advocated by the lecture today remain optimal, even in the much bigger design space where you drop the DSIC condition. So this is one of those scenarios where DSIC is actually for free. Okay? But that won't be obvious from what I say today. Good question. All right, so the main thing we've got to do today is I've got to give you a formula for the revenue. Okay, but so you should be kind of doing a double take. It's like, wait a minute, I just gave you a formula for the revenue, okay? You're right, but so it turns out this formula for revenue it's very hard to figure out what auctions make this as large as possible, okay? So I'm going to give you a second formula for revenue, actually really for expected revenue. So really what we care about is not so much this on a single input V, but rather we care about the expectation of this on average over V. I will give you a second formula, which is also equal to this one, but which is much more useful. Okay? It's basically going to be a much more operational formula that we can understand how to maximize. We can understand which mechanisms maximize it as opposed to this one. Okay? So next, so let's say important second formula for expected revenue of an auction. Okay, so that's the main thing we have to do today. Right, so first we'll derive this formula, then we'll turn on to interpreting it and actually optimizing it in various cases of interest. All right, so what do I want to erase? I want to erase this. No. Erase this. So this second formula for the expected revenue, it's going to be yet another killer application of Meyerson's lemma. In particular, basically we're just going to start from Meyerson's payment formula. Remember, Meyerson's payment formula is what says that given an allocation rule X, there's a unique set of payments P that render it into a DSIC mechanism. We applied that, for example, to get our sponsored search per click payments. So we're going to start from the Meyerson's payment formula and then do some computations, and we'll end up with an extremely useful and operational expression for the expected revenue of an auction. So let me just remind you of the formula. So last week I only stated it for piecewise constant allocation rules. So I stated it this way. So if it's piecewise constant, the allocation rule, we just looked at the various points that it jumped. We looked at its breakpoints. And it was the sum over the breakpoints of the jump in the allocation rule times the position at which that jump happened. So this is the position, and we look at the jump of xi at yj. And here the yj's, remember we always look to the left of the bid that we actually got. So here the yj's are the breakpoints between 0 and the ith bidder's bid. Okay? So that's just straight off the board from last week. Today I'm going to write it a little bit differently, okay? And I'll tell you why. But I'm going to write it in a continuous form. So rather than a sum over breakpoints in this integral, I'm going to integrate over the integral. Rather than looking at the jump of the allocation curve, I'm going to look at its quote-unquote derivative. So look at x prime. And I'm integrating, and I'm looking, again, as usual, when there's an increase in the allocation rule, it gets multiplied, it gets weighted by the position at which that increase happens. Okay? So a couple comments, okay? So, I hope it's clear that there are sort of, you can syntactically match, components of one of these formulas to the other one. In fact, really these are the same formula as long as you have sort of a suitable interpretation of what a derivative means and what an integral means when you have non-differentiable but monotone allocation rules x, okay? So depending on how much of your advanced calculus you remember, either observe or believe me that for the piecewise constant allocation rules we had been focusing on as a motivating special case last week, these formulas are really the same. Okay, but let me tell you why I did it. Okay, so one reason is that in this computation that will give us this very useful formula, there's a couple of sort of calculus-like maneuvers I want to do, like integration by parts, and they'll just look much more natural if I'm working with this sort of calculus-like formula for the payment. Secondly is, there's really nothing special about piecewise constant payment rules. And so last week, when we were young and naive, it made sense to focus on that special case, but with our newfound maturity, maybe I want to give you a version that also extends not beyond piecewise constant rules to arbitrary monotone allocation rules x. For those of you that sort of do remember your advanced calculus and are worried about some pathologies you can get from arbitrary functions x, let me remind you that in mechanism design, the only kinds of allocation rules we ever care about are monotone, okay, and also bounded, right? And basically monotone bounded functions just are kind of almost as good as differentiable functions. Okay, they're differentiable except at a set of measures 0. So it really gives very little trouble in doing kind of whatever we want with these integrals. Okay? All right. So again, Meyerson's payment formula, we're given as input, if you like, an allocation rule x, and this is what the payments have got to be, given that we've assumed DSIC mechanisms. Okay? All right. So good. So here's the plan, okay? So I talked about how the payments directly are difficult to work with. It's not clear how to optimize them. But we've now built up all this comfort doing our surplus maximization, and there we really got some good practice, right? We're like, what allocation rule do we want? Well, let's look at our expression, right? The sum of the VI's times the XI's, and let's choose XI so that this number gets really big. So we have a lot of practice sort of designing allocation rules to maximize expressions of the allocation rules, expressions of the x's, okay? So, at least in principle, the following strategy looks like a good idea. Okay? We don't know how to optimize directly a formula that just involves the prices, the p's, but we feel much more comfortable with the x's, with the allocations. This formula tells us that, well, if what you care about the p's, actually that's sort of a dependent variable on this independent variable of the x. Okay? So this says, if you care about revenue, if you care about money, you can always rewrite it in terms of the allocation rule x. Okay? And that's what we sort of know how to optimize. So in principle, we can take the very simple payment expression, which has disappeared, and rewrite it in terms of the allocation rule. Okay? What's not at all obvious right now is whether that's going to be a fruitful exercise or not. And there's really no way to know in advance without actually doing the computation. So that's what we're going to do next. But that's where we're going. We're starting with this obvious but difficult to work with formula with the p's, applying this to get an expression in terms of the x's, the allocation rules. That will simplify beautifully, and we'll get an expression that we can optimize directly. Okay, so that's the plan. Question? So the derivation, I've broken it into bite-sized steps. for your viewing pleasure. 6 steps, but each is very simple. And actually the last 3 are trivial. Okay? All right, so we're just going to start with the payment formula. So fix a bidder I. For now, fix the bids or the valuations of the other bidders, V minus I. Remember, those are random. Okay? Remember, every VI is drawn from a distribution, so V minus I is from some joint distribution. Okay, but for now, just sort of condition on what it is. Fix V minus I. Okay? I's valuation, we haven't fixed. So I's valuation is random, drawn from Fi. Okay? So by the payment formula, we have, so let's just think about how much money we're going to get from bidder I for a given auction. Okay? So we're starting from, we're given, okay, a DSIC mechanism x comma p. Okay, that's the starting point. Now we're doing some computations with it. So in this auction we're given, how much money do we get on average, what bidder I's valuation is. Well, so now we're just going to expand the payment by bidder I in terms of Meyerson's payment formula. Okay? So that is just equal to, all right, so we just integrate with respect to this distribution. Okay? First of all, so I'm just expanding the expectation. And now we're going to get a double integral because I'm going to further expand PI in terms of that formula. Okay, and so that's sort of our initial expansion step. Then we're going to have 2 steps that simplify it back down. Excuse me while I clear some real estate. Any questions? No questions. All right. So to finish the expansion, step 1 just says holding V minus I fixed, integrating with respect to VI. What we get is a double integral over there. So the outer one is the integral, just because VI's valuation is random. Then we get this integration that we inherit from the payment formula. So this goes from 0 up to I's instantiated valuation, Z times X prime. All right. So that's step 1. And again, this is sort of what we knew we could do in principle. We had a formula with the P's. We had a formula that would, and then we had something that would give us something in the X's, right? But so what? It's not clear if this is useful or not. So now we're just going to apply 2 of those sort of rules of thumb when you're kind of doing computations and seeing if they lead to anything interesting. So pretty much whenever you have a double integral or double sum, and you don't know how to interpret it, check the reverse direction. Okay? Like some of the time it'll make it better. Right? That should be a Pavlovian response for all of you when you see double sums and double integrals. So, step 2. So we're integrating over the joint space of Z's and VI's, right? This is choosing VI, this is choosing Z. Z is always at most VI. So let's reverse the order. Let's have our outer variable be Z. And VI has to be at least Z, so this is going to go from Z to V max. Yeah. And now in the part where we're integrating over VI, I'm going to take the only thing which depends only on VI, which is independent of Z. Okay. So that's our new inner integral. And then we have all the stuff that does depend. Sorry, it should be Z. It does depend on Z outside. All right? And when you're doing these sort of, Pavlovian response, massagings of formulas, you look for signs from above that you're on the right track, right? And we have a sign here suggesting maybe we're doing something smart, which is one of these integrals we can actually just kind of basically forget about. It just becomes something that we have a much simpler expression for, all right, which is this inner one. So what is that also known as? Close. 1 minus capital F. Remember, little f, that's just the density function for the ith distribution. So we're just looking at the mass that's above z, okay? 1 minus fi of z, all right? So that's a good sign. We had 2 integrals, now we have 1. All right, so that's step 2. Here's our last non-trivial step, okay? All right, so we only have 1 integral, so we can't reverse a pair. But now, so we do have something which is clearly a derivative under the integral, right? So that's another Pavlovian response would now be integration by parts. So that's what we're going to do. And with the decomposition, let's just make our life simple. The part of, which is the derivative, which is the g prime, if you like, we'll make the x prime, and then, whoops, f will be the rest of the stuff. So when you integrate by parts, what do you get? You get out pops sort of one integral, which is the f prime g part, and then you also have to evaluate fg at the 2 endpoints. So there's going to be a second term, but let's just look at the part which is f times g evaluated at the endpoints. So when you integrate by parts, yeah. So the first term, right, so we have the f part, and then we have the g part. Yeah. V max to 0. Okay. And then there's something else that we'll work with in a second. But let's just look at this. So what does this thing evaluate to when z is 0? Obviously. It obviously evaluates to 0, right? Because we have a z here as part of the product. What about when z is v max? Also 0, right? So this is going to be 1. Right? V max is as high as z will go. Right? So this is 1, so this is 0. All right? So this whole term disappears, which again is a sign from above we're on the right track. Okay. All right, so what do we get? Now we get the rest of the stuff. 0 v max. So now we have our xi, z, v minus I. Now we need to do a little product rule action on this thing. So what's that going to be? That's going to be 1 minus fi of z plus, whoops, minus z times the density. Okay? So this is where we are. So where did we start? We started for how much money do we expect to get from bidder I on average over v sub I, and we got this. Now the final sort of idea, if you want to call it that, so we're integrating something that looks like it should be with respect to i's valuation, right, from 0 to v max. It feels like this should be an integral over valuation space. So I'm just going to take out the density term, put that in advance, so I can interpret this as an expected value of a random variable with respect to vi. Okay, so but really all I'm doing is multiplying and dividing by the density. So I can rewrite this to be 0 v max I'll distribute some minus signs. Okay, so that's step 3. which at least, it's not looking so bad. We now have a formula that conceivably admits a nice interpretation, and it does. I'm going to explain to you the nice interpretation now. Okay? So again, all we've done at this point, this is just sort of the grunge work we had to do. We had this idea, Meyerson's payment formula should give us a different representation of expected revenue. Maybe it's useful. It's simplified as much as possible. Boom. Okay? So step 4, let's just add some notation to make it look even nicer. Specifically, this thing, we're going to denote this by phi sub I, depends on I, because we're looking at I's distribution here, of Z. Okay? So it's just notation. It has a name, you should know the name, which is a virtual valuation. Okay? I'll talk a little bit about how to interpret this when we get to the end of the derivation. Okay, it does have some nice interpretations. But for now, virtual valuation phi sub I, it's just this thing that pops up in our computation. All right? So, but maybe an example would be helpful, just so you're not too scared of these virtual valuations. So consider, so suppose Fi of Z is Z on 0, 1, i.e. we're looking at a uniform 0, 1 random variable. So the density is just 1. So let's look at what the virtual value is. Well, just by definition, it's Z minus 1 minus the distribution function. That's just the identity function. The density is just 1. So this is just 2Z minus 1. Okay? So we started with the distribution function Z, the uniform distribution. So Z is between 0 and 1 here. It's a uniform 0, 1 random variable. And we get something which is uniformly spread between minus 1 and 1 uniformly. Okay? So again, I haven't told you how to interpret it, but it's not that bad in many cases of interest. One thing I just want to point out, which is going to be useful later. So note, these virtual values can be negative. It is possible that this second term swamps out the first. Right, so again, here if Z is less than 1/2, this is a negative number. So it can be less than 0. Let me summarize what we've proven. So how much money do you make from bidder I? Well, you make precisely the expected value of its virtual value. So what I'm doing now is I'm interpreting Z as a valuation. Okay? Remember, so this is an integral with respect to the distribution f sub I. So it's like Z is a private valuation. It's the same integral. So, right. So how much money do you make on average from somebody? You make the average value of its virtual value times its allocation. Okay? So that's where things stand at the end of step 4. Okay? Agreed? Yeah.
What happened to the x, the xi of z and v minus I when you went to that integral and applying for it?
Where are we at?
So, yeah.
Oh, here. Yeah, I think I just totally omitted it. My bad. Thank you. Thank you very much. Excellent comment. Yep, thank you. Did you like how it kind of went away and then it came back?
Okay, cool.
This is Z. DZ. Thank you. Other questions or typos? All right, so we've done all the grunge work. So now let's just actually see why this is useful, why it has a nice interpretation. So, all right. So step 5. So now we just, so what did we just prove? So we just proved that two things were equal. Whatever VI is, that's underneath. So remember, steps 1 through 4 were all fixing V minus I, or we fix the values of the other people. They're random, but we conditioned on them. And so we said whatever V minus I is, these two averages are equal. Okay, so now we're just going to average more over the V minus I's. They're still going to be equal. So formally, we just apply, we just integrate out over everybody else's valuations. And so the expected amount of money that we get from bidder I, on average, over the inputs, is exactly the amount of virtual value that I is contributing to the allocation. Okay? And now finally, I just use linearity of expectations twice to say that the expected amount of money we make from everybody is the expected amount of these virtual values we get from everybody. Okay? So the average, the expected revenue of the mechanism, so this left-hand side is what we've cared about all along. Right, so we started with an arbitrary DSIC mechanism, allocation rule X, payment rule P. We average over all valuation profiles. The average is with respect to these distributions. We look at the average amount of money we make. So we know this is just the sum of the PIs by definition. That's the revenue. So by linearity of expectation, I can take the sum out. Just look at how much money I make from a single person. For each single person, this is what we exactly characterized in terms of these virtual values. And now I'm just going to push the sum back into the expectation. So this is the second invocation. All right, and this is where I wanted to get to. Okay? So this is the objective we're trying to maximize, the average amount of revenue that the mechanism gets. This can evidently be expressed as a sum of the PIs, and we just did a whole bunch of work culminating in the fact that we can express it in terms of the allocation variables, the X sub i's, which we knew we could do, but the reason we should be happy is it's sort of a fairly shockingly simple formula in terms of the Xi's, which is characterizing the amount of money that we make. And again, here's what's crazy, right? So this objective function, revenue, right? What's it about? It's about payments. That's all it's about. Somehow we just compiled the fact that we cared about payments into a new formula which doesn't reference payments at all. Okay? It's only about the virtual values of the allocation. To drive this point home, squint for a second and suppose that the phi wasn't even there. Okay? So just erase the phi in your mind. What is that expression that's left? It's just the surplus, right? It's a sum over I of VI xi. Right? So if we erase the phi sub I, it would be the average surplus of a mechanism. And that's something we already have a good understanding of how to optimize. So somehow payments, despite being about the entirely other part of a mechanism, the payment rule, not the allocations per se, it boils down to exactly the same thing as maximizing surplus, except instead of VI, you have some function of VI, this virtual value, which, at least in some contexts, like for a uniform distribution, really isn't that bad. You just take Z and you replace it by 2Z minus 1. Okay? So it is not a priori obvious. So I know of no way to easily explain why you get such a magically simple formula for payments purely in terms of the allocation rule. But now that we have it, it's extremely useful. And so that's what I'm going to spend the rest of the lecture explaining. Question?
Would it be possible to get a really quick summary of each of the steps? Like step 3 is integrating my parts. So if it's something
Sure. I mean, I think I wrote on the board as we went along. But so step 1 was you expand in terms of Meyerson payment formula. Step 2 is a reversal of order of integration. Step 3 is integration by parts. Step 4, we introduced the notation for phi sub I. Step 5, what was step 5? It was something simple. Oh yeah, step 5 was just you forget about fixing v minus I and average over v minus I, and then linearity of expectations to finish. Okay, good. So the rest of the lecture, how to interpret this, how do we optimize it? Okay. Yeah.
Why do you assume that your is differentiable?
Excuse me.
Why do you assume that your allocation rule is differentiable?
I didn't. I talked about this. It's monotone. It's differentiable at all, but it measures 0. And you can make all this work. Again, I'm not going to turn this into advanced calculus class, so I'm not going to give you a fully rigorous proof. But all of this can be made precise. All of this can be made rigorous. Okay? So every single step is correct with a suitable background of integration and differentiation, which I'm not going to do here for obvious reasons. Yeah?
If these divides follow the same distribution,
Good question. Good question. Right, so this simplifies. That's right. So that's where we're going to go next. So this computation that we just did doesn't really simplify if you make extra assumptions. It's still like exactly the same length. So this computation I did at a reasonably general level. As far as interpreting what we've done, it does simplify. And so I'll now make extra assumptions so that we get particularly attractive consequences of this theorem. And that'll be a prime example.
but it's a reasonable assumption, right? Because most the variance would be from the same.
It depends. So the question is about what if all of the FIs are the same? And technically you get simplifications. In some applications it's well motivated, and in some it isn't. Kind of depends. But yes, for sure in some applications it is well motivated, and you're absolutely right that it gets simpler. Or what I'm about to say next will get simpler. Okay. Other questions? Yeah.
I just don't understand step 5.
Okay, sorry, yeah, I did that too fast, I'm sure. So steps 1 through 4,
Yes.
we fixed v minus I. And we said that the expected amount of money you make from bidder I is the same either way. Or both the formulas are the same. So if something's true no matter what v minus I is, or if this equality holds no matter what v minus I is, then it's also true for any averaging over the v minus i's that you like. And that's all we did. So so syntactically, all I wanted to do is I wanted to replace a vi in the expectation with the full vector v. So I just integrated out with respect to v minus I.
So what's the v sub I in the virtual function? Or sorry, the virtual value? Which v sub I is that?
Okay, good question. So this is still, so step 5 is still for a fixed bidder I. Okay? So for every I, okay, so steps 1 through 4, we fixed both the bidder and the valuations of everyone else, v minus I. Step 5, we're only fixing bidder I and nothing else. And we're averaging over all of v. Yeah, thanks for the question. Okay. So, again, so in English, what did we prove? I.e., so this is the right way to remember it compactly. For any auction, the expected revenue that the auction produces is just the expected, what's called virtual surplus. For reasons that I hope are now obvious. We agreed that if you hide the phi, this is just expected surplus. Phi just changes the valuation to a virtual valuation. So the expected valuation of this sum is the expected virtual surplus. Therefore, maximizing the left-hand side boils down to maximizing the right-hand side. Okay? So let's call this star. Okay? Yep.
It seems like just like a bit of a how to put this. Since there's a function in there, does that necessarily mean the next maximizing one maximizing the other? Like
these are both numbers. So for a given mechanism, it has an expected revenue, that's a number, 127. And I'm saying the expected virtual surplus is some a priori conceivably different number? And I'm saying it's not. It's 127.
Are they necessarily proportional?
I'm saying they're the same number for every mechanism.
It's the same number.
Same number. So the mechanism which gets the biggest number of the right-hand type is the one that gets the biggest number of the left-hand type, which is what we want. All right. So now let's put this hard work to use. So remember the original motivating question, even just for two bidders, one item, IID uniform, we proposed a couple auctions. One did better than the other, but for all we knew, there were other auctions out there that were still better. How would we ever know if we had an optimal auction? So, as promised, let's now make some extra assumptions just to interpret what we've done. Okay? So, two assumptions. Single item auction and IID. Say all FIs are the same. And as was suggested, if you know nothing else about the bidders, generally you're going to assume they're IID. If you know extra information about the bidders, you have eBay bidding histories, you might assume they're coming from different distributions. Okay? But for now, let's assume they're from the same distribution. Of course, if all the FIs are the same, if you remember the formula for phi sub I, that depended only on FI and little fi. So if the distributions are the same, then these phi i's are also all the same. And remember, what we want to do is we want to choose X. So we're designing the auction, right? It's just like now it's just like when we're doing surplus maximization, right? We can pick any auction we want, and we have some objective function that we want to make as big as possible. And now, for the rest of this lecture, we're going to forget about payments per se. We're just going to focus on making virtual surplus as large as possible. Okay? So we get to choose X. How should we choose it to make that as large as possible? Well, so this is some average, right? So the expectation is over the valuation profiles V. For each profile V, we get some number. We want to make this average as high as possible. But if you think about it, we actually get to define this allocation rule X separately for every valuation profile. Right? So for every vector V, we can choose X, i.e. who wins, however we want. So if you want to make the average of all these numbers as big as possible, the obvious approach is to just optimize point-wise, to make every single constituent number as big as possible. That is, for every possible input, every valuation profile V, make what's inside the expectation as high as possible. Okay? That's the obvious approach to how to choose X to make this number as big as possible. So obvious idea. Maximize star point-wise, by which I mean for each input and an input's evaluation profile, right? It's our allocation rule. We get to define it however we want. So let's just define the allocation rule to maximize the virtual surplus achieved on this particular input. Now in the current example, this is independent of I, but let me just go ahead and write it for now. Okay? So the proposal is to make the expected surplus as high as possible for each input. Make it as high as possible. Yep.
You have to make sure that X is modified.
Good. You're several steps ahead. But you're absolutely right. Okay, so we'll get there. Okay. So let me just make sure. So what I want to point out is that this rule is very easy to understand in the context of a single item auction where all the distributions are the same. Okay? So what does that mean? Okay? So we're a single item auction, so the constraint is just that there's one winner at most. So how do you define X to make this as big as possible? So I give you V, okay, you know everyone's valuations. There are then virtual values, and again, as the seller you know the distributions, so you know the fees. How should you set X to make this as big as possible?
Are we still assuming that, like, I mean, the normal rules from single item auctions apply, right?
Yes, exactly. So, I mean, we're talking about basically X is a 0, 1 vector with the most 1, 1. So what should it be? Yeah.
Item to the highest bidder.
So first, let's it's again a couple steps ahead, I think. So what we really want is the bidder with the highest fee, right? The highest virtual value. Okay, so let's just start with that. So you want to give to the person with the highest virtual value. Okay, well actually that needs a slight modification actually. That needs a caveat. Do we really always want to give it to the bidder with the highest virtual value? Why wouldn't we? Right, so don't forget virtual values can be negative. So remember we had this 2z minus 1 for a uniform distribution. So it went between -1 and 1. Okay? So giving it to nobody is better than giving it to somebody if everybody's negative. This may seem weird at first, but actually remember in our one bidder, one item case, we weren't always giving it to the person. The only way to make any money was to set a price that was some non-trivial amount, which would result in them not always taking the item. Okay, so we actually shouldn't be shocked that sometimes no one will win, given that we want to maximize revenue. Okay, we already have some intuition for that. Good. So i.e., so the winner is the bidder with the highest. Again, I'll just write phi I of vi, even though right now all of the phi i's are the same function. Or no one if all phi I vi's are negative. Okay? Now here's what's obvious, right? So subject to feasibility, subject to only having one item, for every possible value v, we made this number as big as it can be, by definition. Okay? Therefore, we certainly made this average over all of these numbers as big as it can be. Okay? We made this expectation as big as it can be for each constituent contribution, okay, individually. So certainly the average is as high as it can ever be. The catch, however, is, so is this actually legal? Right? Does this actually lead to a mechanism? Is this a bona fide mechanism? And so what could be the problem? The problem is that there's no way to make a dominant strategy incentive compatible. And by Meyerson's lemma, we know the necessary and sufficient condition to be DSIC is for this allocation rule to be monotone. So the important question is, this allocation rule that we just defined, which is certainly optimal if we can implement it, is it implementable or not? Is it monotone or not? Okay? So catch, is this rule X monotone? Okay? So can you maybe think of a simple condition under which this X would be monotone? Like a condition on phi? So if phi is non-decreasing, right? So what's the allocation rule basically? It's basically give it to the person with the highest virtual value. Monotonicity means that if you win and I bring your value up, then you should still win. So as long as bringing your value up only brings your virtual value up, then you'll remain a winner. Okay? So phi being non-decreasing is a sufficient condition for this rule to be monotone. And if you think about it for a minute, you realize it's also necessary. So monotonicity of this rule boils down to phi being non-decreasing. Okay? So the answer, if and only if, so now I'll just write phi, because there's one for the one distribution, is monotone. I've only shown you one example of a phi thus far, which is for the uniform distribution. That was 2v minus 1. Okay? So that's increasing, so that's good. All right? So at least for the uniform case, we know it is monotone. So this actually, right. So I'll just say that. There are distributions that are where phi is not monotone, okay? And then this argument doesn't work, right? So some distributions lead to non-decreasing phis, and some don't. There's a standard terminology for that dichotomy. So we call a distribution f regular if it obeys the condition we want, essentially. So if the corresponding phi, which again is just this function that depends on capital F and its density little f, is non-decreasing. Okay? So on exercise set 3, I'll give you some examples to explore kind of which distributions give you non-decreasing, which distributions are regular and which ones are irregular. Most of the ones you'll find in the back of a statistics textbook are regular, uniform, exponential, Gaussian, and so on. There are distributions which are not, so like bimodal distributions usually are not. And if you have super heavy tails, that will also usually be an irregular distribution. Okay? So in this course, because it's an introductory course where I focus on the most important points, we're only going to ever discuss regular distributions. The theory from this lecture can be extended to all distributions, including irregular distributions, but it requires more work. But I do want you to know that there is a more general theory out there. Okay. All right. So, back to the single item auction. So let's consider the regular case. So suppose f is regular. Even for the moment, assume that phi is strictly increasing, like for a uniform distribution. Okay? When bidders are all the same, and so they have the same function mapping values to virtual values, when we pick the bidder as the winner with the highest virtual value, can you say anything about which bidder we're picking in terms of the values? So by definition, we're picking the bidder with the highest virtual value. Does that happen to also be the highest bidder? If it's regular and if all bidders are drawn from the same distribution? Yes. Okay. So with phi strictly increasing, it means the ordering on virtual values is the same as the ordering on values. So the highest value is the same as the highest virtual value. So the winner, if there is one, is going to be the high bidder in this auction, in this optimal auction. Okay? So the only difference between this optimal auction, where you pick the bidder with the high virtual value, and the Vickrey auction, where you pick the bidder with a high value, is that in this rule here, there will be cases where you pick nobody, okay, if all of the virtual values are negative. So that is the only difference between the revenue maximizing auction for IID regular bidders and the revenue maximizing auction. It's just that sometimes no one will win. Okay? In fact, I claim that this can be explained just through a single reserve price. Okay? So for IID regular bidders, same as a Vickrey auction, so what would be the reserve price in terms of the, right, so 0 is a good answer. The reserve price is 0 in the virtual valuation space. Okay, so in terms of virtual values, that's exactly right. You have to beat 0. So in terms of the actual bids, remember the Vickrey auction is just, it's the high bidder subject to the reserve. Right? So to map back from the virtual values back to the actual bids, like in eBay, you need to take the inverse virtual value of 0. Okay? So with reserve price, phi minus 1 of 0. Okay? So So the allocation rule described here, just give it to the highest virtual value or nobody if they're all less than 0. If it's IID and regular, that's exactly the same thing as giving it to the highest value or nobody if everybody's bid is below phi minus 1 of 0. Okay? For the uniform distribution, recall that phi was 2v minus 1. So what value of v makes 2v minus 1 equal to 0? 1/2. So for the uniform distribution, the inverse virtual value of 0 is 1/2. So for IID bidders, no matter how many there are, drawn from a uniform distribution IID, the optimal auction, okay, among all the auctions that exist in the world, the optimal auction is simply eBay, a Vickrey auction, with the suitably chosen reserve price or opening bid, in that case 1/2. So 2 bidders, 1 item in particular, the reserve of 1/2, which got us 5/12, you can't do better. Okay? No other reserve is better, no other auction format is better. That's always the best you can do. Okay? So, all right, so we have this very general formula characterizing revenue of auctions. It tells us how to derive optimal auctions, which in simple settings actually are, auctions that are actually in use in practice. It's kind of amazing. We optimized over this huge set of auctions. The best one is really just eBay. If they're IID, okay? So the exercises will ask you to do exactly this same thing when the bidders come from different distributions, and you'll find that the optimal auctions can be a little weird, okay? So when people have different distributions, they have different phi sub i's. So when you give to optimize revenue, you want to give it to the bidder with the highest virtual value, the highest phi I of vi. That need not be the bidder with the highest value. Okay? To optimize revenue with non-IID bidders, you fundamentally must move away from always awarding the good to the highest bidder. Okay? The payments are also a little tricky to understand. All right? So that's going to motivate the main topic of next lecture. So now that we've completely solved for the optimal auction in this average case sense for any single parameter environment, we're going to say, well, there are simple settings where this is an auction we might actually use. And there are more complex settings where in principle the theory tells us how to maximize revenue, but they have extra properties or details which we never see in practice, like allocating to bidders that are not the highest. And so the question we'll talk about on Wednesday is using the lens of approximation and saying, can we get almost optimal auctions using practical auction formats? So I'll see you then.